Welcome to our tutorial on linear regression. In this video, we'll dive into one of the fundamental techniques in data science. Linear regression is a statistical method used to model the relationship between a dependent variable and one or more independent variables. Essentially, it helps us understand how changes in independent variables influence the dependent variable. So why is it important? Linear regression serves as a foundational tool in data science. It's used for predictions and also for determining the strength of predictors. Moreover, it lays the groundwork for more advanced models and techniques, making it indispensable for data professionals. Throughout this series, we'll explore the theoretical concepts underlying linear regression, break down its mathematical formulation, and demonstrate practical implementation. By the end, you'll have a solid grasp of what linear regression is and how it can be applied to solve real-world problems. Get ready to delve deeper into the nuances of linear regression, starting with its theoretical foundations. Let's embark on this exciting journey into data science. Welcome to our comprehensive tutorial on linear regression, theory, and implementation. In this segment, we'll lay down the theoretical foundations of linear regression, a cornerstone in data science. Let's start with the basics. Linear regression is a statistical method for modeling the relationship between a dependent variable and one or more independent variables. Understanding these basic concepts is crucial for grasping advanced topics later on. First, we'll dive into the mathematical formulation. At its core, linear regression fits a line through a set of data points, minimizing the distance between the actual data and the line. This line can be described using the equation y equals b plus bnx plus e, where y represents the dependent variable, x is the independent variable, beta so is the intercept, bn is the slope, and e denotes the error term. Next, we'll explore some key assumptions behind linear regression. For the model to be valid, the relationship between the variables must be linear. The residuals, differences between observed and predicted values, should be independently and normally distributed with constant variance, known as homoscedasticity. By understanding these theoretical underpinnings, we set the stage for practical applications. In upcoming segments, we'll bridge these concepts with real-world data and hands-on implementation. Stay tuned as we move from theory to practice and unravel the full potential of linear regression. In this segment, we delve into the mathematical formulation of the linear regression model. The equation y equals beta plus beta and x plus e is our starting point. Here, y represents the dependent variable we aim to predict, while x serves as the independent variable, our predictor. Beta, the intercept, signifies where the regression line crosses the y-axis, the value of y when x is 0. Delta 1, the slope, indicates the change in y for a one-unit change in x. Finally, ev, the error term, captures the variability in y that can't be explained by the linear relationship with x. It accounts for the noise and random errors in our data. Breaking down these components helps us understand how each part contributes to the model. As we continue, we'll see how these theoretical constructs translate into practical applications. Next, we'll explore the essential assumptions underpinning linear regression. For linear regression to provide reliable results, certain fundamental assumptions must be met. First is linearity. The relationship between independent and dependent variables must be linear. Second, independence. Observations should be independent of each other. Third, homoscedasticity. The variance of errors should be consistent across all levels of the independent variable. Finally, normality. Errors should be normally distributed. Without these assumptions, our linear regression model's validity can be compromised. As we move forward, you'll see how these assumptions play a role in the practical application and evaluation of linear regression models. In this segment, let's dive into a simple yet insightful example of linear regression. Picture predicting a student's test score based on their study hours. Imagine plotting data points on a graph where each point represents a student's study hours and corresponding test score. Once these data points are plotted, we fit a regression line to best represent the relationship between the variables. This line helps visualize how increased study hours could potentially lead to higher test scores. The regression line is not just a visual aid, but a mathematical tool that allows us to make predictions. By understanding its slope and intercept, we can infer how much the test score is expected to change for each additional hour of study. As we process these data points and the fitted regression line, it becomes clearer how linear regression helps in making informed predictions based on historical data. Next, we'll explore the more complex realm of multiple linear regression, involving multiple independent variables. In the world of data science, relationships between variables aren't always simple. When one independent variable isn't enough, we turn to multiple linear regression. Here, we incorporate multiple variables to make our predictions, adding layers of complexity but yielding more precise results. Imagine you're predicting house prices. Beyond the size of the house, you might include the number of bedrooms, location quality, and age of the home. Each variable contributes to a nuanced, multidimensional prediction. This complexity demands careful interpretation, but offers richer insights. As a data scientist, mastering multiple linear regression enables you to uncover hidden patterns in your data. It's a powerful tool that, when wielded correctly, enhances your predictive models significantly. As we move forward, you'll see how to practically implement these concepts using Python and real-world datasets. Now, let's implement linear regression in Python. We'll use powerful libraries like NumPy, Pandas, and scikit-learn to make this process seamless and efficient. First, we import our libraries, NumPy for numerical operations, Pandas for data manipulation, and scikit-learn for building and evaluating our model. We'll start by loading our dataset into a Pandas data frame for easy handling and analysis. Once our data is loaded, we need to prepare it for the linear regression model. This includes handling any missing values, standardizing our features, and splitting the data into training and testing sets. With our data prepped, we can now define our linear regression model using scikit-learn's linear regression class. We fit the model to our training data, allowing it to learn the relationship between our features and target variable. After training the model, it's time to make predictions. We use the test data to evaluate the model's performance, comparing predicted values with actual values. This step is crucial as it helps us understand how well our model generalizes to new data. Finally, we interpret the results. Key metrics like the model's coefficients, intercept, and R-squared value provide insights into the model's behavior and accuracy. By analyzing these metrics, we can ensure our model meets the desired performance standards. As we move forward, you'll see how to evaluate the model in more detail, exploring metrics like mean squared error and analyzing residuals. This ensures you have a comprehensive understanding of your linear regression model's performance before deploying it into a real-world application. To evaluate our linear regression model, we need specific metrics to gauge its performance. One such metric is R-squared, indicating the proportion of the variance in the dependent variable that is predictable from the independent variables. Another important measure is the mean squared error, MSE, capturing the average squared differences between observed outcomes and predictions. By scrutinizing the residuals, the differences between observed and predicted values, we can identify patterns that might suggest problems with our model. These metrics are essential for understanding where our model excels and where it might need improvement. Next, you'll see how to address common issues in linear regression. Linear regression is a powerful tool for understanding relationships in data, but it's not without its pitfalls. One common issue is overfitting, where the model captures noise instead of the actual pattern. To avoid this, use techniques like cross-validation and regularization. Another issue is multicollinearity, occurring when independent variables are highly correlated, making it difficult to determine their individual impacts. Address this by checking correlation matrices and possibly removing or combining variables. Lastly, outliers can skew results and lead to incorrect conclusions. Use visual inspections and statistical tests to identify and handle outliers appropriately. Understanding these common pitfalls and knowing how to mitigate them helps ensure your linear regression models are robust and reliable. Stay tuned for our concluding segment where we summarize everything we've learned and discuss next steps in your data science journey. As we wrap up this tutorial, let's review what we've learned. We've journeyed through the theoretical foundations, explored illustrative examples, and tackled the practical implementation of linear regression. To solidify your understanding, I encourage you to dive into more advanced topics and experiment with real world datasets. The world of data science is vast and continuously evolving, and your journey doesn't end here. Engage with additional resources, take on new challenges, and apply what you've learned to real projects. Thank you for joining us. Continue your pursuit of knowledge and innovation. Stay curious, stay driven, and keep learning.